Chapter 16, Kinetics, Rates, and Mechanisms of Chemical Reactions. In this chapter, we're going to discuss reaction rates, the expression of reaction rate, the rate law and its components, integrated rate laws, theories of chemical kinetics, reaction mechanisms, and catalysis. Chemical processes occur over a wide range of rates. An explosion reaction, for example, may take 1 second or less. Fruit ripening may take months. Human aging continues for decades. And the formation of coal from dead plants takes millions of years. For a chemical reaction to occur, reactants must collide in order to react. For example, carbon and oxygen must collide in order to form carbon dioxide. The factors that influence the reaction rate include concentration, physical state, and temperature. The higher the concentration of the reactants, the greater reaction rate. And this is because a higher concentration of reactant particles allow a greater number of collisions. The physical state also influences the reaction rate. Reactants in the liquid phase, for example, react much faster than in the solid state, because in the liquid state, molecules can mix and collide. In the solid state, molecules has a fixed location and cannot move. The higher the temperature, the greater the reaction rate. This is because at higher temperatures, particles have more energy and therefore collide more often and more effectively. Temperature not only affects the collision frequency, but also provides collision energy that is required for a reaction to occur. Let's take this reaction as an example. Ozone, nitrogen monoxide react to form oxygen gas and nitrogen dioxide. Here shows a collision between ozone molecule and nitrogen monoxide. If this reaction takes place at a higher temperature, the molecules has enough energy to break the bond between oxygen in ozone and form a new bond between oxygen and nitrogen. And the result is a product NO2 and oxygen. If the collision occurs at a lower temperature, however, the molecules do not have enough energy to break the bond and form a new bond. So the molecules just bounce off from each other without reacting. Same is here. The collision without forming product, molecules just bounce off from each other. In physics, you learned that speed is defined as distance divided by time. Okay, for example, you may run at a speed of 10 miles per hour, okay, or 5 meters per second. Okay, so the distance is miles or meter, and time is per hour or seconds. So you run 5 meters every second. Okay, that's speed. In chemical reaction, the reaction rate is measured in terms of change in concentration of reactants or product per unit of time. So instead of miles or meter, it's the concentration or molarity. It's the molarity per seconds. Okay, so here is the reaction rate is the change in concentration, change in time. Okay, for example, if we start a chemical reaction, initially the reactant's concentration is 5 molarity. So that's the initial concentration. And if the time we start the reaction is, let's say, 10 seconds, so that's the time we start the reaction. Okay, Now, when the reaction finishes, the reactant is consumed. Only 10 molarity, 2 molarity concentration left. So this is the final concentration of the reactants. And when we stop the reaction, the time is, let's say, 30 seconds. Okay, so this is the time when we stop it. Okay, so how much time the reaction used? Okay, how much time it take for the reaction to finish? Well, you use 30 minus 10. So in this equation, T2 minus T1. So that gives you 20 seconds. So that's how much time it takes for the reaction to consume concentration from 5 to 2. And so what is the change in concentration? It's the final to minus 5. Okay, and 2 minus 5 is negative 3. All right, so in order for the reaction rate to be positive, we add a negative sign here. So negative concentration change, because the concentration decrease. Okay, so that gives you 3 divided by 20. All right, and that gives you 0.15 molarity per seconds. Okay, divided by time, seconds. So which means every seconds the reaction consumes 0.15 molarity of the reactant. Let's use this reaction as an example, and ozone as a reactant. This table shows the concentration of ozone at different time. For example, at the beginning, time 0, concentration is 3.2 times 10 to the minus 5. Based on this table, we can plot here the concentration of ozone as a function of time. The first point is here, where time is 0, concentration is 3.2, and then times 10 to the minus 5 here. Okay, and when time is 20 seconds, from the table we can see concentration is 1.95 times 10 to the minus 5, and on the plot is this point. Okay, well, time is 20 seconds, concentration here, right, this point is 1.95 times 10 to the minus 5. So increase time, decrease concentration of ozone. And this is because with time, some ozone is consumed, so it becomes product. And so the concentration of ozone decrease. How do we calculate the reaction rate? Well, if we want to find the reaction rate for the whole process, we use the concentration of the at the 60 seconds, that's the final concentration, minus concentration at the beginning, divided by 60 seconds. Okay, and that gives you the reaction rate for the whole process. And this rate is called average rate. Okay, in mathematics, we can calculate the slope of this line that passes these 2 points, the first point and the last point. And that slope of this line is the average rate of the whole process. In this case, is 3.5 times 10 to the minus 7. We can also calculate the average rate for the first 10 seconds. So this is the range from 0 to 10 seconds, the range. So that average rate is shown here, the green line that passes the first point and this point at 10 seconds. The slope is the average rate. And in this case, it's 7.8 times 10 to the minus 7. And we can similarly calculate the average rate at the last 10 seconds from 50 to 60 seconds. And we draw the straight line past the 2 points. And the slope is 1.3 times 10 to the minus 7. So these are all average rate, okay, at a different range. How do we calculate the rate at one point, okay, or at a certain time? For example, at 35 seconds, what is the reaction rate at this point? Okay, this is called instantaneous rate. To calculate the instantaneous rate, we can choose a range around this point. Okay, calculate the average rate, but then we decrease the range. So for example, here is 10 seconds, so the range is 10 seconds, and then we decrease to 5 seconds, decrease to 2 seconds, to 1 second. Eventually, the range becomes 0, and that becomes 1 point. And the average rate at that point, okay, it becomes instantaneous rate. In mathematics, we draw the tangent line of this point. The slope of this tangent line is the instantaneous rate. So in this case, it is 2.5 times 10 to the minus 7. Now the instantaneous rate at the first point, the beginning, so shown here, E, the tangent line, purple line, the slope is the instantaneous rate at the first point, and that's called initial rate. Okay, and the initial rate for this case is 10 times 10 to the minus 7, which is the highest than any other rates. In general, initial rate is higher than any instantaneous rate at later times. And this is because at the beginning, you have lots of reactants, and so you have highest reaction rate. With time, reactants are consumed, so the concentration becomes smaller and the reaction rate decreases. In the last slide, we show that ozone concentration decreases with time. Similarly, the other reactant, C2H4, also decreases with time. The products, on the other hand, increase with time, because with time, reactants are consumed, products are formed. When we write a reaction rate, for the reactants, we have a negative sign here in front of it, because the change is negative. So for example, for the ozone or C2H4 initially, so let's say at this point, the concentration is 5. At a later time, it becomes 2, it decreases molarity. Okay, so when we use final, which is 2 minus 5, and give you negative. So for the reaction rate to be positive, we must add a negative sign for the reactants. Now for the product, let's say oxygen, at this point is, let's say 1 molarity. At a later time, it increased to 3 molarity. So 3 minus 1 is 2, is positive. So there's no negative sign in front of this expression for reaction rate for the products. Okay. Also, let's look at the stoichiometry for this reaction. So whenever 1 mole of C2H4 is consumed, 1 mole of ozone must be also consumed, and 1 mole of C2H4O must be produced. At the same time, 1 mole oxygen is produced. So the point is, every second, the rate change for each of these substances must be the same. So they have same reaction rate. So the reactants, the product increase just as fast as the reactant decrease. Let's look at another reaction. So hydrogen iodine forms hydrogen iodide. The reactant hydrogen decreases with time. The product hydrogen iodide increases with time. Now if we look at the stoichiometry, 1 mole hydrogen is consumed, 1 mole iodine is also consumed, which will form 2 moles of hydrogen iodide. And that means the reaction rate for hydrogen iodide must be twice as fast as the hydrogen and iodine. For example, if the hydrogen consumption rate is 0.1 molarity, then iodine must also be 0.1 molarity per second. Okay, and the product will be 0.2 molarity per second, because here you have a 2 here. Okay, now in this expression, this is for hydrogen reaction rate for hydrogen iodine. Okay, and this is for reaction rate for hydrogen. And note you have a negative sign because it's reactant. Okay, you have a negative sign. And hydrogen iodide rate is twice of it. So you have 2 up here. Same thing is here. This is for with negative sign. That's the reaction rate for iodine. As a reactant, you have negative sign, and it's twice of this. So the product here is twice of the reaction rate for the 2 reactants. Another way to do it is right here. This is the reaction rate for hydrogen, and this is the reaction rate for iodine. So hydrogen, iodine, and this is the reaction rate for hydrogen iodide, and this is half of it. Okay, hydrogen iodide is twice of hydrogen, and the hydrogen rate is half. You divide by 2. Okay, so in general, the reaction rate depends on what substance you have. You are referring to. So if you say reaction rate for hydrogen, then the reaction rate will be half if you say the reaction rate is for hydrogen iodide. So you need to know what substance you are talking about, the reaction rate. And if you have a reaction rate for a substance, you divide by the coefficient. So in this case, hydrogen iodide has a coefficient 2. If you divide by 2, that will be the same as the reaction rate for other substance. In this case, they have coefficient 1, so they divide by 1, so they are the same. Sample problem 16.1. And this question is about this chemical reaction. Hydrogen, oxygen forms water. The question A asks you to express the rate in terms of changes in hydrogen, oxygen, and water with time. And B, when oxygen is decreasing at this rate, at what rate is water increasing? To express the rate in terms of change in concentration with time, we need to remember for the reactants we have a negative sign. And also, we need to divide by the coefficients. So here, for oxygen, you have a negative sign because it's reactants. Hydrogen also have a negative sign, but divided by the coefficient. Okay, because hydrogen rate is twice oxygen. Okay, so this one is twice of oxygen. But if you divide by 2, then that becomes the same, called the rate of reaction. And for water, you also divide by 2. Okay. Next one, if oxygen is decreasing at this rate. Okay. So if you look at the stoichiometry, we know water formation rate should be twice oxygen. So if oxygen is 0.23, then water must be 0.23 times 2. Another way to do it is that we look at this equation. So we have half water reaction rate equals oxygen reaction rate, okay, which is given, all right? So we can calculate reaction rate for water. You need to times 2 because you times 2 here and you times 2 here. So 2 cancel, and that gives you the rate for water. This is the rate for water. And the answer is 0.46 moles per liter per second. As we showed in the last slide, in a chemical reaction, the reaction rate for different substances may be different. But for a particular rate, if you divide by its own coefficient, so A rate divided by A, and the B reaction rate divided by coefficient B, and C divided by C, so then they have the same value. And these expressions are called reaction rate. In this way, the rate does not depend on what substance we use. They're all the same. As I explained at the beginning of this chapter, reaction rate is affected by the concentration of the reactants. The higher the concentration, the more collisions molecules make at a unit time, the faster reaction goes. For a simple reaction such as A goes to product, reaction rate can be written as a constant K times concentration raised to a certain power. K is called rate constant. A is the concentration of reactants. N is the reaction order. For some reactions, okay, the reaction rate is K constant times A raised to the first order. Okay, these reactions are called first order reaction. An important feature of first order reaction is that when you increase concentration twice, the reaction rate also increases twice. It's linear. For example, if the reactant's concentration is 3 molarity, then according to this equation, the reaction rate is K times 3, so 3K. Now, if the concentration increases to 6 molarity, then the reaction rate becomes K times 6, so 6K, which is twice of the initial reaction rate. So if this is R1, this is R2. So you see R2 is twice R1. If the concentration increases twice, the reaction rate also double. Okay. Now for some reactions, the reaction rate is K times A raised to second power, and these reactions are called second order reaction. For second order reaction, if concentration increases twice, the reaction rate increases 4 times. Okay. For example, again, if concentration is 3 molarity, the reaction rate R1 is 3 squared. Okay, so K times 3 squared, so it's 9K. All right. Now, if reaction concentration increases to 6 molarity, so R2 becomes K times 6 squared. So that's 36K, which is 4 times K1. Okay, 4 times 9 is 36. All right. So the rate quadruples when the concentration doubles. Okay, the rate depends on A squared for a second order reaction. Now for other reactions, the reaction rate may be written as K times A to the 0 power. Okay, as we know in mathematics, anything raised to 0 power is 1. For example, 5 to the 0 power is 1. Okay, and therefore this is just K. So reaction rate is just a constant K. It does not depend on the concentration. So if the concentration double, the reaction rate does not change for a 0 order reaction. This diagram shows the plots of reactant concentration versus time for the first, second, and 0 order reactions. For all these reactions, the concentration decreases when time increases. So concentration decrease. However, for the first order reaction, the decrease slows down as time goes on. And for the second order reaction, the decrease slows down even more. For the 0 order reaction, the decrease does not change as time goes on. In the last slide, we showed how concentration changes with time. In this slide, we show the plots of reaction rate as a function of concentration for first order, second order, and 0 order reaction. For the 0 order reaction, the plot is a horizontal line. This is because the reaction rate is just a constant K, as I showed in the last slide. So the reaction rate does not change when you change the concentration. For the first order reaction, the plot is an upward sloping line because the rate is directly proportional to A, to the concentration. For the second order reaction, the plot is upward sloping curve because the rate increases exponentially with the concentration of A. Sometimes a reaction may involve several types of reactants. For example, here, nitrogen monoxide reacts with hydrogen gas to form nitrogen gas and water. So two types of reactants, and the reaction rate must be affected by both of these two reactants. Experimental data shows that the rate law reaction rate is a constant K times the concentration of NO raised to the second power and the hydrogen gas raised to the first power. So in this case, we say this reaction is the second order with respect to NO, nitrogen monoxide, but the first order with respect to hydrogen. So hydrogen is the first order, NO is the second order, and 2 plus 1 equals 3. So the overall reaction is third order. And note that the reaction is the first order with respect to hydrogen, even though the coefficient for hydrogen in the balanced equation is 2. So if you look at this balanced equation, the overall reaction, the coefficient is 2. But the rate law shows that the reaction is the first order instead of second order. In other words, you cannot predict the rate law just by looking at the coefficient of the balanced reaction equation. The reaction order must be determined from experimental data. Sample problem 16.2. For each of following reactions, use the given rate law to determine the reaction order with respect to each reactant and the overall order. For reaction in A, determine the factor by which the rate changes if nitrogen monoxide is tripled and oxygen is doubled. In question A, in rate law, NO is raised to second power, oxygen raised to the first power, and therefore the reaction is second order with respect to NO, first order with respect to oxygen. And 2 plus 1 equals 3, so it's third order overall. When concentration of NO tripled and oxygen doubled, the reaction rate is K, which is a constant that doesn't change, but the concentration of NO becomes 3 times initial concentration, all right, and together squared, okay, because the new concentration is 3NO, and the new oxygen concentration is 2 times oxygen, and then it's first power, okay? So now the numbers square, so 3 square is 9, okay, and 2 to the first power is 2, and the rest is just the K times NO times squared times oxygen, okay? So K times NO squared times oxygen is just the reaction rate before change, okay? And the 2 times 9 is 18. So if we write the final rate is prime, so R rate prime becomes 18 times initial reaction rate. Okay, so the rate increased by a factor of 18. And next question, the rate law is K times the concentration to the power 3/2. And therefore the reaction is 3/2 order with respect to these reactants. And the overall is 3/2. And next question, so hydrogen peroxide is one reactant raised to first power. Iodide also raised to first power, okay? Please pay attention not to look at the coefficient, look at the rate law. So it's first order with respect to hydrogen peroxide, first order with respect to iodide, okay? There's another reactant, hydrogen, which does not appear in this rate law, and therefore it's zero order with respect to hydrogen. This This sample problem again shows that rate law cannot be predicted by the coefficient of the balanced overall reaction. For example, in C, iodide has a coefficient 3, but the rate law is the first order with iodide. And the hydrogen ion has a coefficient 2, but it doesn't appear in rate law, so it's a 0 order with respect to hydrogen ion. Rate law can be obtained by either experiment or by mechanism we're going to discuss later. Let's see how we use experiment to determine rate law. So here shows a general reaction. Reactants A, reactants B, so A plus 2B forms C and D. We already know that we cannot predict rate law by looking at the coefficient. So the rate law in general should be a constant times A to the mth power and the reactants B to the nth power. Okay, remember m not necessarily to be 1 and n not necessarily to be 2. It has to be determined by experiment. Okay, one example is here. Oxygen react with 2 nitrogen monoxide forms 2 nitrogen dioxide. So the rate law can be written as a K constant times oxygen to the mth power, nitrogen monoxide to the nth power. And we should do experiment to determine what is m, what is n. Okay, so we run a series of experiments in which one reactant concentration changes while the other is kept constant. Okay, so for example, we keep NO constant, so this part doesn't change. We only change oxygen concentration, and so we measure reaction rate. How does reaction rate change? From that we can find M. Okay, by changing oxygen, measure rate law, we can find N, and then we keep oxygen concentration constant, change NO, and then we measure reaction rate, and then we find N. So here is the results of 4 experiments. So in experiment 1, okay, we let A concentration to be 2.5 times 10 to the minus 2, and the B is 3 times 10 to the minus 2. So we make this mixture, okay, AB mixture with known concentration. We measure the reaction rate, which is 1.75 times 10 to the minus 3. Okay, so now we do the second experiment. This time we keep B the same. You see, B doesn't change, but we change A to be twice concentration, and then we measure its reaction rate. So here is the experiment reaction rate. Okay, and then in experiment 3, we keep A constant. We change B to be twice. Okay, so A constant, B twice, and measure the reaction rate. Okay, in experiment 4, we keep here A constant and B twice. We again measure reaction rate. Okay, and then from this information we can deduce N and M. Okay, so we'll see how we do it. Let's compare experiments 1 and 2. These 2 experiments have the same initial concentration of B. Okay, but A change from 2.5 to 5 times 10 to the minus 2. And the initial rate also changed from 1.75 to 3.5 times 10 to the minus 3. How do we use this information to find M or N? Okay, now first let's calculate rate change in theory. Okay, note that this is the rate change by experiment. In theory, we should look at this equation to calculate. So here we have equation, the ratio of rate 2, experiment 2 over experiment 1. Okay, and according to theory, rate 1 should be k times a 1, okay, to the mth power b1. So a1 is this one. So a1, okay, this is b1. All right, and this is a2, experiment 2 concentration, and this is b2. Okay, now you can just use the numbers, these numbers. But for simplicity, we use the symbols. And you will see here, these two are the same. B1 equals B2. So in this ratio, these two cancel each other because they have the same value, 3 times 10 to the minus 2. Also, K constant are the same. The only thing changes is A2, A1. So the rate 2 over rate 1 in theory should equal to A2 to the mth power divided by A1 to the mth power. Now in math, this can be written as just A2 over A1 to the mth power. They have the same exponent. So for example, 5 to the second power, 2 to the second power, you can write 5 divided by 2 to the second power. Okay, so in theory, so this is in theory, the ratio of experiment 2 over 1 reaction rate. Okay, now let's substitute with the numbers. So A2 is this one, 5. So 5 times 10 to the minus 2. Okay, A1 is this one. So that's the ratio of reaction rate in theory. Now, what is the ratio in experiment? We look at these two. So that's 3.5 times 10 to the minus 3 or 1.75 times 10 to the minus 3. So this is by experiment and this is by theory, and these two should equal. Okay, now this, if you calculate, it's just 2. And the right side is 2 to the mth power. So that's the theory, that's the experiment. For these two to be the same, m has to be 1. So by comparing experiment 1 and 2, we found m, okay, the power of A. Okay, so what we did is that we keep B constant. By keeping B constant, in this equation, we can ignore B. We just look at A and M. And so by comparing in theory how the reaction rate change with experiments, the data by experiment, then we can find the power of M, the order of A, concentration A. Let's compare experiments 1 and 3. And this time, they have same concentration of A, but B is different, and therefore the reaction rate are different. As last time, we first calculate the theoretical rate change from 1 to 3. So we calculate the ratio of reaction rate 3 over reaction rate 1 by theory. So using the rate law. Okay, again, and this is A3, this is A1, and this is B1, and this is B3. Okay, according to the rate law, and so here is the rate for 3, experiment 3, here is the rate for experiment 1. And this time, A3 equals A1, and so A cancel each other, and K also the same. Reaction rate constant doesn't change. So what we have now is B3, okay, to the nth power divided by B1 to the nth power. And again, we can write as B3 divided by B1 to the nth power. All right, so here, this is by theory. Okay, by theory, the reaction rate ratio is the concentration of B3, so this one divided by B1. Okay, that's the theory prediction. And experimentally, we get, this is the reaction rate for 3, and this is the reaction rate for 1. And so we have this ratio. And use the calculator, and you will find the left side is 2, the right side is 2 to the nth power. So for this equation to be equal, n has to be 1. Okay, so that tells us that rate law is the first order with respect to B. Okay, so this time we keep A constant. We look at B change, and we found the rate order for B. In summary, in this sample problem, we first look at experiment 1 and 2, which has same concentration of B, and therefore the reaction rate change only depends on A, because B is the same, B concentration are the same, so B doesn't contribute to reaction rate change, and therefore the rate 2 over 1 is only A, 2 over A1, but to the mth power, because you have m, okay? And since the concentration changed twice from 2.5 to 5, so the ratio is 2. So 2 to the mth power, and that's the theory. And then we look at the experiment, it's also twice, and that gives you m equals 1. And then we look at experiment 1 and 3. So these two, and they have same concentration of A, so we omit A, and the reaction rate only contributed by B. So now R3 over R1 equals B concentration 3 over B1 to the nth power. And again, so B from 1 to 3 concentration doubles. So in theory, the rate ratio should be 2 to the nth power. And then we look at the experiment, these two experimental data from 1.75 to 3.5 times 10 to the minus 3. So again, it's twice, it's double. The reaction rate also double. And that shows us n must be 1. Okay, now you may ask, when can n equals 2? Well, if compare 1 and 3, okay, 1 and 3, and we keep B or A constant. So again, A is constant, the same. Now B also doubles. So this, in theory, this is the same because we increase concentration of B twice. But then when we measure reaction rate, this is the data. In fact, if it's from 1.75 to 4 times 1.475 times 10 to the minus 3, and then equals 4. So this is the theory, and this, if this is the experimental data, the reaction rate increase 4 times. Okay, in 4 times. Then for 2 to the nth power to becomes 4, then n has to be 2, and then it is a second order reaction. Now, if the reaction rate measured change 9 times, so it's 9 times. Okay, the concentration again doubles. So this is the theory, and this is experiment. Then n will be third power. So it will be a third order reaction. Okay. Now I also want to point out that this line, the experiment 4, in this case is extra information that is not necessary. Okay, because we only need 1, 2, 1, 3, we get m and n. However, you can also choose, for example, 4 and 3. If you choose 4 and 3, then you will see they have same concentration B, so you don't look at the B, and from A you can find m. All right, so you can. So there are many ways to solve this sample problem. One more thing I want to point out, that when you measure reaction rate, in reality, there are different types of errors. So instead of here, when you calculate the ratio 2 over 1, you get exactly 2. In reality, you may get 1.99 or 2.101. So in this case, you approximate the reaction rate is just 2. And then here, by theory, it's 2 to the m's power. And so m equals 1. Okay? Now, if you measure the reaction rate ratio to be 4.05 or 3.985, so in that case, you approximate to be 4. Okay, so 4 equals 2 to the m's power, then m is 2. So that would be a second order reaction. The unit of rate constant K depends on reaction order. For example, if it's a first order reaction, R equals K times A. The unit of R is always molarity per seconds. Okay, the concentration change per seconds. Concentration is molarity. So molarity per seconds. Molarity is moles per liter. So for reaction rate is moles per liter per seconds. Okay, so that's the unit for reaction rate. If it's a first order reaction, then this should equal to K times Ka. The unit of concentration is moles per liter. Okay, so if you compare this equation left and right, so the left side has per seconds, and therefore K must has a unit per seconds. Okay, or seconds to the -1 power. Okay, now in general, you can calculate the unit of K by the reaction rate unit divided by the concentration part. Okay, for example, if it's a second order reaction, R equals K to the A squared, okay, second power, then the unit K should equal to unit R, which is mole per liter per seconds, divided by the concentration part unit, which is moles per liter squared, means you do twice, so mole per liter. Okay, so 1 cancel, mole per liter, and you have 1 more. So that give you, so you divide by mole per liter. So now liter is here. So liter per seconds per mole. Okay, so that's the second order reaction. Liter per mole per seconds. Now, if it's a zero order, okay, zero order R equals K, because A to the 0 power is 1. All right, so that's the zero order. Now, this tells us that the unit of K should equal to the unit of R, and the unit of R is mole per liter per seconds. Sample problem 16.3. This question is about this reaction, and the rate law is here, and the goal 1 is to find M and N, okay, and B, we need to find K. So from last sample question, we already know how to find M and N. We need to compare 1, 2, 1, 3 to find M and N, and then we'll choose one experiment to find the K. To find M, we choose experiment 1 and 2 because they have same concentration of CO, and so the only contribution to the reaction rate is NO2 concentration. Okay, and therefore in theory, the reaction rate 2/1 should equal to the only concentration of NO2 to the of the experiment 2 divided by NO2 to the of experiment 1, because CO same, K same. Okay, now note that in this case, the concentration increased 4 times instead of twice in the last sample question. So in theory, okay, this is the reaction rate ratio, which is 4 to the m's power. Okay, reaction concentration changing 4 times, so 4 to the m's power. Now, experimentally, this is the data, which is 0.08 divided by 0.005. And using calculator, you will find it's 16. So 16 equals 4 to the m's power. One way to find m is by guessing. So first try m equals 1. Okay, and you will find the right side is 4 to the 1 power, which is 4. So the equation doesn't work. All right, so this is not the answer. Then try m equals 2. So m equals 2, the right side, 4 to the second power is 16. And therefore, that's the correct answer, m equals 2. Okay, more formally, we apply log on both sides. So the left side becomes log 16, and the right side becomes log 4 to the m's power. In math, the power can go in front of log, so you have m to the log 4. Okay, to calculate m, you use log 16 divided by log 4, and that gives you 2. So the conclusion is the reaction is the second order in NO2. To find the n, we choose experiment 1 and 3 because they have same concentration of NO2. So we can ignore NO2 and only look at carbon monoxide concentration change. All right, so the reaction rate is only determined by this concentration. The ratio of 3/1 reaction rate should equal to concentration of CO of the experiment 3 divided by CO of experiment 1 to the nth power. Okay. Now note that NCO increased twice. So by theory, okay, you should have 2 to the nth power. Okay, increase twice. So 2 to the nth power by theory. By experiment, this is the data, and you'll find that 1 and 3 have the same reaction rate. So the ratio is 1. So this is 1. So for this to be 1, n has to be 0. Okay, so that means carbon monoxide has a 0 order. Okay, now we already know m equals 2 from last slide. And so the reaction rate law is K NO2 to the second power, CO to the 0 power, which is just 1. And therefore we have K NO2 to the second power. So the overall reaction is a second power, a second order. From part A, we already find out the reaction rate law is K times NO2 to the second power. If you choose any of these 3 experiments, for example, choose 1, we know the concentration of NO2 in this equation. We know the reaction rate in the left side, so we can calculate the K. All right, so K can be calculated by the rate divided by NO2 to the second power. And so it's the reaction rate in the experiment 1 is 0.005, and the concentration NO2 in experiment 1 is 0.1 and need to be second power. Okay, so using calculator, you get K is 0.5 liter molarity per second. Sample problem 16.4. At a particular temperature and volume, 2 gases, A, which is red, and B, which is blue, react. The following molecular scenes represent the starting mixtures for 4 experiments. Experiment 1, the initial rate is given here. Experiment 2, the reaction rate is also given here, and the 3, reaction rate. And the question is, what is the reaction order with respect to A and B and the overall reaction order? From the last 2 sample problems, we can solve this type of questions by looking at the concentration change. Okay, so we assume the reaction, because you have 2 reactants, so the reaction rate should be rate constant times A to the mth power and the B to the nth power. Okay, now in this case, we don't have concentration, but we can count the numbers. For example, if we compare these two experiments, they have same blue, okay, both are 2. And so that means B are the same, okay? And the only change is A. So A changed from 2 to 4. So 2 to 4 is twice, okay? And then we look at the reaction rate change. So we look at the theoretical change, we had calculate the experimental change, then we can find M. All right. Similarly, if we compare these two, we can find N. Okay, we'll see in the next slide. As I explained in the last slide, experiment 1 and 2 has same number of B. So the reaction rate ratio 2/1, okay, B cancel each other. So only A, number of A, experiment 2 divided by A, experiment 1. And the ratio is 4 divided by 2. So in theory, should be 2 to the mth power. And the given numbers should be 1 times 10 to the minus 4 divided by 0.5 times 10 to the minus 4. Again, this is 2. So for these two equal, m is 1. So we get the order of A is 1, first order. Okay, first order for A. And then we look at experiment 1 and 3. Okay, and 1 and 3 had the same number of A. So the reaction rate ratio A cancel. So you get B, only B. And the B is again is 2 to 4. So 4 divided by 2 is again 2 to the nth power. The experimental data given is 2 times 10 to the minus 4 divided by 0.5 times 10 to the minus 4. And that's 4. So for 4 equal to 2 to the nth power, n has to be 2. So it's a second order with respect to B. And therefore, the overall order is 1 plus 2 equals 3. In part B, it asks us to write the reaction rate law. From part A, we already know the reaction is first order with respect to A, second order with respect to B. So the reaction rate law should be Ka times B to the second power. In part C, it asks us to predict the reaction rate for molecular scene 4. Okay, there are many ways to do this question, but one way is we choose molecular scene 3, and compare these two. Okay, we found out that they have same number of B. So this is B. You have 4 here. You also have 4 here. So same number of B, and therefore the reaction rate will only change when A changes. So here in 3 you have 2 of them. So 1 is 2, and the other for 4 you have 4 A's. So from 3 to 4, the concentration or number of A doubles. Okay, according to rate law, it's a first order reaction. When concentration double, the reaction rate also double, and therefore we predict the reaction rate should be the reaction rate for 3 times 2, and the answer is 4 times 10 to the minus 4. So far we have discussed the rate laws. For first order reaction, the rate law is reaction rate equals Ka. A is the concentration of the reactant A. Second order reaction rate equals K times A squared, and the zero order reaction rate equals K times A to the 0 power, or just K. These rate laws are very important because they tell you how fast reaction go. They allow you to calculate the reaction rate if you know the concentration. In kinetics, there's another type of question, and that is, after a certain time, for example, 30 seconds, what is the concentration left? In other words, we want to know the concentration at a certain time. Now, this type of question can be answered by the integrated rate law. So this is the rate law for first order reaction, and this is the integrated rate law for the first order reaction. In this equation, the left side is natural log. A naught is the initial concentration of A. And this is the concentration of A at a certain time. For example, at 30 seconds. What is the concentration? This is the one. Equals, the right side is K, is the rate constant, times T. Okay, so if this is 30 seconds, then this will be 30 seconds. What is the concentration? Okay, there are different versions of this equation. Okay, for example, we can add a negative sign on both sides. So negative ln A naught AT equals KT. Also negative sign. So you add negative sign on both sides. Okay. Now on the left side, okay, if you have negative sign, the negative coefficient can go here as a power. So you have natural log A T to the negative power. Okay, for example, if you have 3 ln 2 equals ln 2 to the third power. So this goes as a power. Same thing is here. Now negative power 1 means you can inverse it. So instead of A naught, you write AT A naught. Okay, so just inverse it, which equals KT or negative KT. So you add a negative sign. So here you have a negative sign. Okay, you add a negative sign on both sides. Okay, all right. So based on the definition of natural log, okay, if this equation natural log equals negative KT, then this one A T over A naught should equals to E. Okay, that's what the natural log mean. Okay, that means this fraction should equals to base E to the negative KT power. Okay, so this equation is equivalent to this one. It's just mathematics modification. So these two are equivalent. Now we can multiply by A naught on both sides. So what you get is this equation. A at the time T equals A initial concentration times E to the negative KT. Okay, so this is the equation again equivalent to this equation. So when we say integral rate law for the first order reaction, we refer to either this one or this one. They are the same. It's just mathematics modification. So what the advantage of this one is that if you know time for the 30 seconds, then you can calculate. You just use this equation to calculate the concentration of A. So which equals initial concentration times E to the negative KT. So plug in initial concentration, plug in K, plug in T, and you get the concentration at 30 seconds. Okay, so it answers the question, what is the concentration at a certain time? So that's the first order reaction. Okay, now if it's a second order reaction, how do you calculate concentration at a certain time? Let's say 30 seconds. You cannot use this equation anymore because this is only for first order reaction. Okay, so let's see the integral rate law for the second order reaction. Okay, so here is the integral rate law for the second order reaction. All right, so this is rate law and this is the integral rate law. Okay, so in this equation, the left side is inverse of the concentration A at a certain time. And this is inverse minus inverse initial concentration equals KT. All right, so again, if you want to calculate the concentration after 30 seconds, then this equation you can move this to the right side. So 1 over A naught AT equals, okay, negative sign becomes positive. So KT plus 1 over A naught. Okay, so plug in time, K, initial concentration, then you can calculate the concentration of a certain time. So that's the second order reaction. What if it's a zero order reaction? Okay, if it's a zero order reaction, you cannot use either this or this. You cannot use neither of these two. So there's a integral rate law for zero order reaction. Okay, that's this one. All right, so this is the rate law for zero order reaction, and this is the integral rate law for the zero order reaction. Okay, again, if you want to know the concentration at 30 seconds, then you can modify this, becomes AT equals A naught minus KT. So plug in time, K, initial concentration, then you can calculate the concentration at a certain time. Sample problem 16.5. At 1000 degree, cyclobutane decomposes in a first order reaction. So this is a key word, first order reaction, with the very high rate constant. So this is K to 2 molecules of ethylene. The question is, A, the initial concentration is 2 molarity, so this is A naught, initial concentration. The question is, what is the concentration after 0.01 second? So it asks you the concentration, so this is concentration at a certain time, t. T is 0.01. So this tells you that we need an integral rate law. Okay, remember rate law will answer question how fast reaction go, and the integral rate law answer question is what is the concentration after a certain time. So for first order reaction, okay, you choose this equation. This is for first order reaction. Now in the last slide we derived the equation, and that is the concentration equals at a certain time equals initial concentration times E to the negative KT. Okay, I mentioned that these two are equivalent, just mathematical modification. So you can directly plug in all the data. So time here is 0.01 seconds, and K is this number, all right, and A naught is 2 molarity. So if we plug in everything, you should get the concentration at 0.01 second. Okay. Now you may also step by step plug in. So A naught over AT in this case is the cyclobutane initial concentration, and this is the concentration at a certain time. In this case, is natural log 2 divided by the concentration that we want to calculate. And the right side is the KT. So here is the K, here is the T, and multiplication give you 0.87. So if natural log equals 0.87, according to the definition, then this should equals to E to the 0.87 power. Okay, so that means this is E to the 0.87 power. Okay, so in mathematics, if ln A equals B, then A equals E to the B's power, and that's why you get this equation. Okay, use a calculator that give you 2.4. So to calculate this one, all right, you can use 2 divided by 2.4, and that give you 0.83 molarity. In question B, it asks you how long will it take for 70% of cyclobutane to decompose. So if 70% decompose, so how much left? It would be 30% left. Okay, so the concentration will be, initial concentration is 2 multiplied by 30% or 0.3, and that gives you 0.6 molarity. So now the question is, how long, what is the time for the concentration to become 0.6 from 2, this is initial, so this is A0, to become AT. We want to calculate the time. Okay, so here is the integral rate law for the first order reaction. In this case, we know K. Okay, we know initial concentration, we know final concentration. We want to calculate time. Okay, let's plug in the numbers. So ln 2 divided by 0.6 is the left side. On the right side is K times T. T is unknown. To calculate T, we divide by 87 on both sides. So that gives you this equation. T equals 1 over 87 times natural log 2 divided by 0.6. Now use the calculator, you will get 0.014. Now I want to point out that in this question, we have a simple way, okay? Because if you look at this equation, the left side, all you need is the ratio. So you don't actually need the numbers. And so you need the ratio, and let's say this is initial concentration, and the final concentration is 30%, so 0.3% of A0. Okay, so if you know 70% consumed, then 0.3 left, 0.3 times initial, okay, which equals 1 over 0.3. And so you don't need to calculate concentration at the time is 0.6. So this step is not necessary. If you know how much percent left, okay, then you can just calculate the ratio. You get this one, which equals KT, 87 times T, and then you can calculate the T. You should get the same answer. Let's look at the first order reaction integral rate law again. In mathematics, if you have ln A divided by B, you can write ln A minus ln B. So this equation, you can write ln A0 minus ln A at the time t equals kt. Okay, so modify this equation. You should get this one. So ln A at a certain time equals negative kt plus ln A0. All right. Now in mathematics, this equation y equals kx plus b, called the linear equation. This is because if you plot y over x for this equation, you should get a straight line, and the slope is k. All right. Now, if k is a negative number, or the slope is negative, then the straight line looks like this. Okay, y decrease with x. So if you compare these two equations, you can see this is actually a linear equation where the y is ln A at a certain time, and t is x, okay, and slope is negative k, and this is intersection. So intersection in this dot, that's the b. Okay, so that means if we do an experiment, we measure A as a function of time, different A. If we plot, okay, if we plot ln A against time, so different time, different A, you plot this curve, you should get a straight line, and the slope, according to this first order equation, integral rate law, the slope is negative k. And this is one way we can find the reaction rate constant by experiment. All right, you measure concentration at different time. You plot ln A as a function of time. You get a straight line. The slope is negative k. Let's look at the second order reaction integral rate law again. So this equation, we can move inverse A naught to the right side, and you get this equation. Again, let's compare with the linear equation. Y equals kx plus b. Okay, so you see, for the second order reaction, y is 1 over a at a certain time. So that's y. And again, t time is x. If you plot 1 over a, okay, if you plot 1 over a as a function of time, just like here, y over x, you get a straight line, and the slope is k. All right, the intersection is 1 over a naught. So again, this is an experimental method to find the slope, find the reaction rate constant for the second order reaction. And you plot inverse concentration over time. Remember, for the first order reaction, you plot ln A as a function of time. You should get a straight line and negative k. So that's the first order reaction. For the second order reaction, is the inverse concentration over time, is a straight line, and the slope is k. Here is the integral rate law for the zero order reaction, or this equation. Okay, so compare with linear equation y equals kx plus b, and so this time y is the concentration itself, and x is t. So if you plot the concentration over time, and you get a straight line, the slope is negative k. Okay, so compare with the first order, second order reaction. First order reaction is a natural log a over time. You get a straight line, and the slope is negative k. And the second order reaction is inverse concentration over time, and you get a straight line, and the slope is k. And the zero order reaction, you plot the concentration itself over time. You get a straight line, and the slope is negative k. Here shows an example of graphic determination of reaction order. Okay, so this reaction is the decomposition of N2O5. And we measure the concentration of N2O5 as a function of time. For example, at the beginning, time 0, the concentration is 0.0165. After 10 minutes, the concentration decreases to 0.0124. And then you measure the concentration at 20 minute, 30, 40, 50, 60 minutes. Okay, so the question is, how do you find out if the reaction is first order reaction, or is it a second order or zero order based on this data? Okay, in the last slide, we showed that if a reaction is a first order reaction, then we can plot ln A as a function of time. You should get a straight line, and the slope is negative k. But if it's a second order reaction, then it's the inverse concentration as a function of time. You get a straight line, and the slope is k. Okay, now if it's a zero order reaction, we plot the concentration itself against time, and you get a straight line, slope is negative k. So in order to find whether it's the first order, zero order, second order, we plot these three curves. Okay, we already have the concentration, we can plot this one. But in order to plot these two, okay, we add two more columns. One is the natural log, one is the inverse, and then we use this as y, or this one against x. Time is x. So plot, make three plots, see which one is a straight line, and then we can tell if it's first order, second order, or zero order. Okay, so here are the plots, and this is the concentration as a function of time. Now this is a not straight line, so this is not zero order. Okay, now second plot is natural log over time, And you can see it's pretty good straight line. So that indicates it's probably first order reaction. And the inverse concentration over time is not a straight line, so it's not a second order reaction. And therefore the conclusion is this reaction is first order reaction.